Today we will talk about common misconceptions in electronics. We will analyze 10 popular myths and bust them both theoretically and in practice. You can easily repeat all the experiments demonstrated in this video at home. So let's do it! This is Ron Martino. Myth number 1. Electricity follows the path of least resistance. I bet you have heard this statement. Of course, there is some truth in it, but it is often taken too literally. This diagram shows a voltage source, a switch, and two resistors. Their resistance is different. R1 is 100 ohms, while R2 is 10 ohms. Which resistor do you think current will flow through after we close switch S1? If we follow the above statement, it's the R2, because its resistance is 10 times lower than the R1. And this answer is, of course, incorrect. The current will flow through both resistors, but it will be distributed in inverse proportion to their resistances. And it's very easy to calculate. Let's use Ohm's law. I equals U divided by R. Current flowing through R1 will be 5 divided by 100, 0.05 amperes. For the R2, it will be 5 divided by 10, 0.5 amperes. It turns out that the current, just like the resistance, will differ exactly 10 times. In general, this relationship is described by Kirchhoff's first rule, which reads as follows. The algebraic sum of currents in a network of conductors meeting at a point is 0. In our case, this means that battery current equals IR1 plus IR2, which is 0.55 amps. So the current flowing into the node, that is the point of connection of the elements, does not select one resistor with the lowest resistance, but is divided between them, in inverse proportion to their resistance. Myth number 2. When replacing a charger, you must choose a device that has a current rating that is no higher than the original. This misconception is probably due to the fact that current is often confused with voltage. Indeed, when you choose a power supply, you must ensure that it is, first of all, rated for the same voltage as the original. If it is lower, your device will be underpowered and most likely not start. And if it is higher, you risk damaging it. This rule, however, does not apply to current strength. Let's conduct a simple experiment. We have two USB chargers in front of us. The voltage, naturally, is 5 volts in both cases, but one charger is rated for a current of 1 amp and the second is 1.5 amps. We will power the light bulb from these power supplies and observe the current value on the ammeter. So, when powered from a 1 amp unit, the current is set at 0.51 amps. What's going to happen if we connect the second 1.5 amp unit? As you can see, the ammeter displays the same 0.51 amps. How to explain this? And why the measured current strength does not correspond to that indicated on the charger? The fact is that the current does not depend on the power source, but on the load connected to it. It is directly proportional to voltage and inversely proportional to resistance. On the other hand, the values indicated on the chargers are the maximum current that this device is capable of delivering. If the voltage and load are the same, the current will also be the same. This obvious conclusion follows from Ohm's law. I equals U divided by R, where U is voltage and R is resistance. Because both power supplies output the same voltage, the U's will be identical. R is the lamp's resistance. We got the same lamp, which means the resistance will also be the same in both cases. From this we can conclude that the current strength will also be the same. Your smartphone will behave exactly the same way. So, whenever choosing a power supply, a charger for a phone or tablet, provided that the voltage is the same, Feel free to choose a unit with a higher amperage. Do not believe the stories that the charger with a higher current rating will damage the battery faster. This assertion is baseless. Myth number 3. When batteries are connected in parallel, the capacity increases, but when batteries are connected in series, it does not. There are two batteries in front of us. In the first, the cells are connected in parallel, and in the second, in series. The capacity of each cell is 1000 mAh. What will be the capacity of these batteries? Perhaps you won't be mistaken if you answer that it's 2000 mAh and 1000 mAh respectively. However, there's a problem here. What is capacity? In the practical sense of the word, it is the amount of energy that a given current source can store and deliver to the load. The main unit of measurement for the production and consumption of electrical energy is the watt-hour. And we are trying to compare amp-hours. Let's calculate the capacity of our two batteries in watt-hours. To do this, we have to simply multiply the voltage and current. Mind you that milliamps must be converted to amperes. So the result for the first battery will be 1 plus 1 multiplied by 3.7, 7.4 watts-hour. And for the second, 1 multiplied by 3.7 plus 1 multiplied by 3.7, also 7.4 watts-hour. So it turns out that the capacity of these two batteries is identical, and connecting them in series leads to its doubling in the same way as parallel connection. If that doesn't sound convincing enough, imagine a huge Tesla car battery made up of 16 blocks consisting of more than 400 18650 cells each. Inside one block, the batteries are connected in series. If we believe the statement that a serial connection does not increase the battery capacity, it turns out that the capacity of 400 cells will be equal to the capacity of one battery. That's absurd, agree? The same thing, by the way, applies to power tool batteries. If you're out shopping for an electric screwdriver and see two models with 3000 mAh 14 volts and 3000 mAh 18 volts batteries in front of you, which battery will have the higher capacity? Of course, the second one, since it can provide the same current strength at a higher voltage and therefore produce more power. I hope that after watching this video, the choice will be obvious to you. Myth number 4. Ferrite cylinders on the cable are needed to protect against external interference. If ferrite is removed from the cable, the device will not work properly. In fact, it's exactly the opposite. Ferrite filters serve to suppress electromagnetic radiation from the cable itself and protect the external environment from its interference. Let's stage an interesting experiment. I'll take an old Super VGA cable, fortunately there's an abundance of this stuff now and everyone throws it away, and extract the ferrite cylinder from it. Then we will need a radio transmitter. You can use any radio remote control operating in the range from 200 MHz and above, as well as a simple detector using two germanium diodes with an LED and a wire soldered to them. When the wire is connected to the antenna and a radio signal is transmitted, the LED flickers. It's flashing because this remote is designed to control a smart home system and the radio signal is modulated with a digital code. But in our case, it doesn't matter. Let's see what happens if we wrap the wires around a ferrite cylinder. As you can see, now the LED is not lit, although the remote control continues to work, as shown by its own indicator. So we can conclude that the task of ferrite filters is to suppress high-frequency radiation arising in the cable itself and to protect surrounding devices and instruments from it. Myth number 5. Any computer password can be hacked. You just need to hire a good specialist. This myth arose most likely under the influence of movies, where an advanced hacker whose face is illuminated by the flickering of the monitor, quickly moving their fingers over the keyboard, hacks the program and in a matter of seconds finds the password. In reality, it doesn't work that way. Indeed, if you happen to have a password-protected program at your disposal, in theory, by disassembling it, that is, restoring its source code, you can find the stored password in it. The same applies to the server that you managed to get access to. But the thing is that passwords are no longer stored in clear text, neither in programs nor on servers. The server usually keeps the encrypted version of the password. When the user enters a password, the server also encrypts it and compares already encrypted copies of the two passwords, after which it decides whether the user should be granted entry into the system. Probably the question should arise here: is it possible to decrypt an encrypted password? The answer is no, it is not, because a one-way ciphering function is used, which means you can convert X to Y, but you cannot convert Y to X. How does that work? Let me give you a very simple example. Imagine that we have two integer prime numbers. Let's say these. Can we multiply them? Sure, any computer can handle this task in a split second. You can see the result on the screen. Question: how can we obtain factors from this product? Let me emphasize that there is only one correct answer here, since the numbers are prime and cannot be factorized by themselves. The only method is ordinal search. However, if the factors are, for example, 1000 digits long, the search can take years. Now consider this. 1875893845033 is the password, and it is saved in the database in the form of a number that you see on the screen. How will you find the password if you know this number? The answer is, you won't. By the way, these days, hackers, because hacking computers has become too difficult, are much more likely to resort to social engineering. They simply call gullible people and leach sensitive information. This is exactly how telephone scammers, known to everyone today, operate. Myth number 6. In diode testing mode, the multimeter shows resistance. Actually, no. In diode testing mode, the multimeter shows voltage. The voltage that drops across the diode you are measuring. And proof of this is the V icon in the upper right corner of the device display. For example, in this case, the drop is 0.17 volts, since it's a Schottky diode. On a regular diode, the drop is 0.73 volts, and on an LED, it drops 1.7 volts. It is actually possible to measure the actual resistance of a diode in a particular circuit, but it is pointless, and soon you will see why. We have the simplest circuit in front of us. An incandescent lamp is powered by a 6-volt source, and a Schottky diode is connected in series with it. To find out the diode resistance, we will apply Ohm's law. So the current in this circuit is 0.54 amps, and the drop across the diode is 0.35 volts. So R equals U divided by E, 0.35 divided by 0.54 is 0.65 ohms. That is, if we install a resistor with such resistance in this circuit, we would get the same result. But let's raise the supply voltage to 8 volts. The drop on the diode is still 0.35 volts, but the current has increased and is now 0.64 amps. It turns out that the diode resistance has changed and is now 0.35 divided by 0.64, 0.54 ohms. This happens because the diode is a semiconductor device with a nonlinear VI characteristic. As the current increases, it reduces its resistance in order to keep the drop at the same level. Since for a particular diode, the drop value is basically unchanged, it is one of its main characteristics. That is why when measuring diodes, the multimeter displays voltage drop rather than resistance. You can learn more about the functions of the multimeter in my video How to use the multimeter. As usual, the link will be in the description. Myth number 7. The LED is current-driven, not voltage-driven. This phrase can be heard very often, and it often literally stupefies newbies. How can you apply current rather than voltage? We supply 220 volts to the lamp to make it glow. We supply 5 volts to the smartphone so that it charges. We supply 12 volts to the car starter to make it start the engine. How is it possible that current, not voltage, needs to be supplied to the LED? And how can this be done? Let's do an experiment. I will be connecting the LEDs to a lab power supply. Please note, without a current-limiting resistor. Then I'll slowly increase the supply voltage, and we'll see what happens. We will start with the red LED. It does not light up. I keep raising the voltage. As the value approximately 1.8 volts is reached, the LED begins to glow. What happens next? With a slight increase in voltage, for example to 1.9 volts, the current strength begins to grow rapidly, as does the LED brightness. At a voltage of 2.08 volts, the current is already 20 mA, and at 2.11 volts, 30 mA. Let's take another LED. This is a blue one. We see that when the voltage reaches 2.3 volts, it doesn't even turn on. The glow starts at approximately 2.4 volts. The current begins to increase. At a voltage of 2.74 volts, it is 10 mA. 2.98 volts, 20 mA. 3.15 volts, 30 mA. Let's take the next test subject. This is a green LED. Here the glow begins at approximately 1.88 volts. At a voltage of 1.95 volts, the current increases to 10 mA, 2.02 volts, 20 mA, 2.08 volts, 30 mA. And the last test subject is the yellow LED. It starts to glow at a voltage of approximately 1.8 volts. 1.97 volts, current 10 mA. 2.02 volts, 20 mA. 2.09, 30 mA. What conclusions can be drawn from this experiment? Of course, each LED does have a voltage at which it operates. But this voltage is very difficult to find, since it is within very small limits. If you lower it, the brightness drops sharply. If you raise it, the current rapidly increases and the LED may fail. Meanwhile, you probably noticed that the higher the current, the higher the brightness. It turns out that when powering an LED, it is more convenient to rely on current rather than voltage, because in this case, we do not have to stabilize it so carefully. Now I will configure the lab power supply differently. I'll set the current limit to 20 mA and the voltage limit to 3.5 volts, and we'll try to power all of our LEDs one at a time. Here goes the green one. We see that the LED is glowing and the voltage is set at 2.05 volts. The yellow one, the same 2.05 volts. Looks like these two have similar characteristics. The blue one, voltage is 3.18 volts. And finally the red one, 2.16 volts. What conclusion can be drawn from all this? Indeed, it is convenient to power LEDs by setting a current limit rather than by supplying a specific voltage. The easiest way to do it, as you probably know, is to connect a resistor in series. That's why they call it current limiting. However, this does not mean that there is no specific voltage for each LED from which it can be powered without the help of a resistor. Simply from a practical point of view, when powering LEDs, it is convenient to rely on current strength rather than voltage. That's what they mean when they say that LEDs are current-driven and not voltage-driven. You can learn more about the properties of LEDs from my video how to power any LED and not turn it to smoke. You will find the link in the description. Myth number 8. The supply voltage of the USB port is always 5 volts. Okay, here we got a regular USB charger, a USB cable, a smartphone, and a device called USB tester. It can display the voltage and current flowing through the cable. I am connecting the charger to the wall outlet and inserting a USB tester into it. Nothing unusual happens. As expected, the tester displays 5 volts. And now I'm plugging the charger into the phone. Let's see what happens now. Miracle! The charger increases voltage to 9 volts. What does it mean? It means that the fast charging protocol has been activated. The principle underlying it was formulated many years ago by Nikola Tesla, who invented his famous alternate current system. The idea was that on the transmitting side, at the power plant, the voltage would be stepped up using a transformer, and on the receiving side, stepped down. What for? The thing is that the amount of energy that can be transmitted through wires of a certain gauge is limited by the maximum current they are able to withstand. You've probably come across a table connecting wire gauge with the maximum current strength. For example, a current of no more than 19 amps can be passed through a copper conductor with a cross-section area of 1.5 square millimeters. If it is exceeded, you can expect overheating, insulation failure, and fire. The same goes for the USB cable. Modern smartphones have powerful processors and batteries of large capacity. And the current that can be transmitted through a standard USB cable is not enough to charge them quickly. But charging requires power, not current. And power is the product of voltage and current. If we cannot increase the current, its value depends, as mentioned above, on the wire gauge, nothing prevents us from increasing the voltage. This is exactly what we observe in the so-called fast charging mode. It should be noted that USB version 3.1 allows the voltage to increase up to 48 volts and the current up to 5 amps. So the power transmitted via USB cable can reach an incredible 240 watts. By the way, the latest MacBook Air, which nowadays uses a standard USB Type-C connector for charging, is charged with a voltage of 14.4 volts. I discussed this issue in more detail in the video Fast Charging and How It Works. The link will be in the description. Myth number 9. The inductor at the output of a step-down converter serves to smooth out the ripple. Here's a diagram of a standard car USB charger built on an MC34063 DC-DC converter and producing 5 volts at the output. As you can see, the input voltage of this stabilizer can reach 25 volts. What do you think is the purpose of inductor L at the output of this circuit? I'm sure 9 out of 10 people will answer. It's obvious. We have a switching converter in front of us. Therefore, the inductor is installed here to smooth out the output ripples. However, this theory instantly fails if you ask the question, how exactly is the voltage stepped down then? We have 25 volts at the input, but there is no transformer in the circuit. So, the inductor here is responsible for accumulating energy and not for smoothing out the ripple. Let's look at a simplified equivalent of the circuit. S1 is a transistor used to switch the inductor. Let's say there is 10 volts at the input of the circuit, and we want to get 5 volts at the output. S1 closes and current begins to flow through the inductor. However, the voltage across the load does not increase instantly because the inductor takes some time to charge. It accumulates energy inside the core. The polarity of the voltage on the inductor at this moment is like this. When the inductor core is saturated, the voltage begins to increase at the load. As soon as it reaches 5 volts, switch S1 opens. At this very moment, a surge of opposite polarity occurs at the inductor, due to which positive goes here and negative goes there. All the energy accumulated in the inductor goes to the load, passing through the VD1 diode, while the output voltage, thanks to the capacitor, retains its value of 5 volts. This converter cannot be called either forward or flyback, since it does not have a transformer. Still, it is a very big misconception to consider that the choke at its output serves simply to smooth out ripples. You can find out more about this topology in my video, How a Step-Down DC-DC Voltage Converter Works. You will find the link in the description. And finally, myth number 10. In Europe, the voltage in the wall outlet is 220 volts. Well, isn't it? It depends. Here is the wall outlet sine wave. What do you think its amplitude is? Let's find out with a simple experiment. We'll connect an oscilloscope to the outlet and check it on the graph. For safety, we will assemble a simple divider with 3 resistors. Their values will be 100K, 22K, and 100K. The voltage across the 22K resistor should be approximately 10 times lower than the input voltage. 3 resistors are needed to obtain a relative decoupling of the output from the input, that is, to ensure the safety of the experiment. If it turns out that the common wire in the oscilloscope breaks through to the phase line, nothing terrible will happen, since the voltage will simply drop across the resistor. Ideally, we should have used 99K as R1 and R3, but I don't have such parts at hand. This is where the case from an old mobile phone charger comes in handy. The divider is ready. Let's measure the voltage first using a multimeter. OK, outlet voltage is 230 volts. And what do we got at the output of the divider? It's 23 volts sharp. We have built an almost perfect voltage divider by 10. So here comes the moment of truth. Let's connect the divider output to an oscilloscope. So here's our sinusoid. The scale is graded with value of 1 division equal to 10 volts. And now let's count voltage from 0 to the peak. What do we see? 32. That means the real sinusoid amplitude is not 230, but 320 volts. Why? Have we been deceived all this time? Of course not. 230 volts is the so-called RMS value, which stands for root mean square. But the amplitude value of the sinusoid is what we're now observing on the oscilloscope, that is from 0 to peak, is 320 volts. But why all this confusion? Why not indicate the real, that is, amplitude value? The reason is the amount of energy that a sinusoidal alternating current source can deliver to the load. It is less than when powering the load with direct current of the same voltage, since AC turns on and off, while DC powers the load continuously. And it is precisely this difference that's compensated by indicating the RMS voltage, based on the actual work it does. For example, if you power an electric heater from a DC source with a voltage of 220 volts, it will produce exactly the same amount of heat as when powered by AC with an RMS value of 220 volts. The amplitude value of this AC sine, accordingly, will be 320 volts. This also explains the little secret of the increased voltage after the bridge rectifier and capacitor. Of course, the capacitor is charged to the amplitude value of the sinusoid, which gives the illusion of an increase in voltage. All measuring instruments, including multimeters, are of course aware of this secret, and when measuring alternating current, reduce the resulting value by a fixed factor, which, by the way, is equal to the root of 2. And that would be it for today. If you find this video useful, please don't forget to give me a thumbs up, comment, share and subscribe. And if you'd like to drop me some Bitcoin or Ether, you can find the links in the description. This was Ron Martino. See you soon.